That speaker is here, and we can start. Georgii, please.
Okay, thank you. So my today talk will be devoted to the problem of constructing coalescing strong stochastic flows on metric spaces.
F when restricted to the ball plus 1 minus p of the E correction variance.
Okay, so the main object of consideration in this talk is I will call it a strong stochastic flow of mappings. So this is the general definition. Let us consider a locally compact separable metric space M. Then a strong stochastic flow on M. It is a family of random mappings, which is jointly measurable. Measurable in all arguments. It satisfies the strong flow property and has independent and stationary increments. So here I like to point that I want a strong flow property to be satisfied without exceptions in omega. If evolutionary property is satisfied with probability 1 when exceptional set can depend on R, S, T, and X, I will say that it is a weak flow. The standard way to describe the distribution of the stochastic flow is to define its finite point motions. So assume that we have a stochastic flow on M. Then for a point X in the M to the power N, let us define Pnt of xb. It is the probability that the flow takes points x1, xn into the set B during the time t. Then from the independent stationary increments and the flow property, we deduce that Pn is a transition probability. Such transition probabilities must be consistent. So there are two properties. So the first means that if we know endpoint motions, then we also know k-point motions for k less than n. And the second property means that if we consider like the same point, then the flow will always take it to the same place. Then the general problem is the following. So if we have a consistent sequence of transition probabilities, can one construct a strong stochastic flow that has prescribed distribution of finite point motions? So this question is of interest because it is known that general stochastic flows can have a complicated structure, like they can generate non-classical filtrations. So the regularity of general stochastic flows is of interest. What regularity we can achieve in the general case. And another motivation is that when we have a strong flow, it often indicates that we can consider some random dynamical system. And in such way, we can get examples of singular random dynamical systems and then analyze them. My work...
Georgii, let me ask you about the second statement or second sentence. What about the noise when you have this strong flow, or even strong flow, and you want to have random dynamical system? You usually want to have the shift of the noise, yes?
Yes,
And
exactly.
what about the noise? Can we say something good about the noise, or noise can be still arbitrary?
In my opinion, to the best of my knowledge, it is an open problem. The idea is when we have a strong flow, then we have already some good measurable structure. So then we can try to shift it. But to construct random dynamical system, it is additional work must be done, because we need to define some good probability space.
But do you have an examples where the noise, where this can be done, and the noise is not Levy noise? Say?
Yes, we have examples of Ratia flow when we can construct random dynamical systems.
Okay.
But it is interesting to know that there are not so many bad examples. So, okay. My work is mostly based on two results. So the first result in this direction was obtained by Darling. He proved that consistent, when we have a consistent family of transition probabilities, then we can construct a family psi. It is a family of random mappings. It has strong flow property, but in his construction, mappings are not measurable. So this is the first result, and the second obtained by Lejean and Raymond. Additionally, we assume that transition semigroups Pn define Feller semigroups, and then they proved that there exists a weak stochastic flow. Now it consists of measurable random mappings, measurable with respect to x and omega. And just to mention that for flows of solutions to smooth stochastic differential equations, it is well known that such flows exist. Okay, so I will recall my first result in this direction. It was obtained for the real line. We additionally assumed three more properties for transition probabilities. So this property, it is continuity of trajectories. The second is an estimate on the meeting time. And the third is absence of atoms. And then we were able to prove that there exists a strong stochastic flow. And actually, in this case, we constructed random dynamical systems. In this talk, I want to generalize this statement for metric graphs. Already on my previous talk here, I discussed some generalization, but it requires too strict assumptions on transition probabilities to be applied. And today I will try to relax these assumptions. So now I describe the space on which I will work. In this talk, M will be a metric graph. It is, by definition, it is a path-connected separable metric space such that we have at most countable set of vertices. Edges are isometric to intervals on the real line, and each vertex has a finite degree. So these are two examples of graphs. In my considerations, I will I will not distinguish the vertex and the point on the edge, because every point on the edge can be considered as a vertex of degree 2. Okay, so now assumptions on transition probabilities. So first of all, the notation such P and X will denote the distribution of a Feller process on the of n-dimensional Feller process on M with starting point X and the transition probabilities Pn. Okay, so we assume as usual the first three assumptions. So consistency, Feller property. Assumption number 4 is the same. It is continuity of trajectories. And assumption number 5, it postulates immediate coalescence. So here I assume that for any compact set K and any positive T, the probability that I have at least C points in the image that start. So I have n points that start from K, and in the image I have at least C points. So it converges to 0 uniformly in all starting points and all numbers of starting points. We already discussed some sufficient conditions. For example, when we can estimate the meeting time on a single edge. If we can estimate the meeting time, we can estimate the probability that the trajectories didn't meet up to time t by increment of some continuous monotone function. When we consider starting points on a fixed edge, then we know that this immediate coalescence property is satisfied. Also,
but let me ask you, this upper index E means that this function can depend on the edge.
yes, yes.
Mm. But what happened if you ref-headed structure, for example, it is compact, but it has a lot of smallest and smallest edges. Yes, and degree of the vertices increases. Yes, and you have this like tree, but tree which is like compact. Yeah. And then suppose that this function m are much bigger and bigger on the smallest edges. Yes.
So edges, edges by definition they must be open in the graph. So we will not have such situation, and every vertex has finite degree. So we
yes, but degree can increase, or you must have some additional condition on this degree.
No, so this is a property 5. It is a local property. It is enough to prove it in the neighborhood of every point.
Yes. Yes,
so,
but you have not only neighborhood like this point is vertex, but you can have a neighborhood where a lot of very small edges exist. Yeah, from different points.
No, each edge is open in the metric space, so it is already its own neighborhood. So by definition, they cannot. The metric is
maybe I can just try to write what I mean. I mean the following situation. Suppose that we have this one, and then smallest, and here a lot of small, and then smaller, and smaller, and on every such small edge, you will have a big function m with big increments. What happened in this small neighborhood? Yeah.
I think that it is not so important here, because let's for example consider
Of course, if you have a regular graph like this one or something like this, then you cannot expect such problem. But finally,
okay, so if we consider a point which is not a vertex, then it lives on the edge. It lives on
yes.
some edge, and it has it's like a base of neighborhood of this point is an interval.
But I see. Okay.
So if they are close, like on the picture, in the metric, these edges will not be close.
Or you just mean that you calculate such metric, such distance along the edges. Yeah?
Yes.
Yes. So this is not
Yes, it's like some kinds of geodesic maybe distance.
I see. Okay. Now it's
So
much more clear.
this
Yeah.
is important.
Okay. Thank you.
Okay. So yes. So there are some sufficient conditions, and I will, at the end of the talk, I will also speak about some other sufficient conditions for property 5. Okay, now I want to prove the theorem that under these conditions, one can construct a strong stochastic flow on the space M. The approach is the following. I consider, first, I consider the skeleton of the flow. By the skeleton, I understand a sequence of trajectories that start from a countable number of points. So here, Pn are starting times, they're rational numbers, and Zn are starting points. They belong to some dense set S. From Kolmogorov theorem, we can prove that there exists a sequence of continuous processes that has that has the same property as trajectories from the flow. Yes, so every finite number of such processes is a continuous failure process with finite point motions given by Pn. So I will refer to this as a skeleton of the flow, and then the idea is to choose appropriately trajectories that start from not from this set. To do this, to do this, I prove the following lemma.
Georgii, and what is Fs?
It is a sigma field generated by trajectories of y up to time s.
Okay. Of all of y's?
Of all y's, yes. Okay, so this is the first result. Assume we have some other complete separable metric space. Then there exists a measurable function L, so it takes a sequence of points of x into a point of x with the following property. If the sequence is relatively compact, then the value is a limit point of this sequence. The proof of the lemma. First, let us consider the compact case. Case of actually this proof was done by Lejeune and Raymond. So consider the space of sequences from 0 to 1. Then we can define this mapping, this measurable selection mapping directly. So the idea is the following. We take the first coordinates, compute the lim sup for the sequence of first components, and find the subsequence that converges to x1. Then for this subsequence, we find the upper limit of second coordinates and choose a subsequence that converges to x2, and so on. As a result, we get some sequence in K, and it is a limit point, and we can construct these subsequences in a measurable way. So this is the rule how to construct subsequences. Okay, now in the general case, when we have a complete separable metric space, it is known, okay, we can choose a mapping that homeomorphically maps X into K, into a subspace of K. For example, like this. And this mapping F, it has a measurable inverse. Because of the Lusin-Suslin theorem, so F is injective and continuous, so it maps Borel sets into Borel sets. Okay, so we have the mapping F, and we have inverse mapping. Okay, it's not inverse, it's like it's left inverse. And then we can define the needed mapping L as the composition of G, L tilde, and F. So F to the power n, it maps sequence in X into sequence in K. Then L tilde gives us some element of K, and G gives an element of X. So the mapping is measurable. Now, if we assume that the sequence is relatively compact, then the image of the closure is a compact in K. So if I apply L tilde to f of x, it must be a limit point, but its value belongs to f of v. So then when I apply the mapping G, it is exactly the inverse, which is continuous. So this proves that mapping L takes any relatively compact sequence into its limit point and is measurable. I will use this result to choose to construct trajectories in the flow that start from all points. So I will apply it to the space of path. By X, I will denote such union. So it is a union. It is all continuous functions with values in M that start at all real numbers S. So by I of F, I will denote the starting time. And by E of F, I will denote the continuous extension of F to the real line. On the space X, I introduce the following metric D. So it measures the distance between starting times and uniform distance on compacts between functions. Then with respect to this metric, X is a complete separable metric space. So there is a measurable selection mapping this space. Okay, and then we can before constructing the flow, I need some properties of the skeleton of the flow. Okay, so the first property is a coalescing property. So if I can construct the skeleton in such a way that if two trajectories met, they stay together after this. So it follows from our assumption number 3 on transition probabilities. Next property is that trajectories from the flow from the skeleton that started before time s, they form a dense set at time s. And the third property, for any compact and any moments of time s less than t, trajectories that passed through k at time s coalesced into finite number of points at time t. So the first is easy. It follows from our assumptions. Second, it was discussed several times already. Essentially, it is a one-dimensional result because we only need to know what happens on one edge, because edges are dense. So in one-dimensional case, we know that such property, it follows from our continuity assumption. And property number 3. So here, this property, it holds with probability 1 for any compact and any moments of time s less than t. So let me explain why it is so. It is enough to consider some neighborhood of some point, and we can assume that we have a neighborhood of a vertex v, and a neighborhood it just consists of several segments. By the property, by this dense property, I can find trajectories that in some interval s minus delta s plus delta, they lived on the edges, like above these segments. Okay, and let us extend the intervals ij. So I extend these intervals to make them I extend these intervals to contain all these trajectories. And this extended neighborhood I denote by K1. Now I fix 2 moments of time, S1 and T1. These are 2 rational moments. And observation is the following, that if trajectory belongs to K at time S, it must belong to K tilde at time S1. Because trajectory, it cannot like jump above these trajectories from the skeleton. So if this set is infinite, then this set is infinite. Okay, and this set, it already depends on the rational points S1 and T1. So this consideration makes possible only for fixed compact and for fixed moments of time to prove this property, and then it follows from our property number 5. Okay, so now I turn to construction of the flow. So let us choose some sequence that converges to 0. So it is a sequence of positive numbers. And for any starting point Sx, I consider following indices. So the sequence Nk, index Nk, it is the first, it is the number of the first trajectory from the skeleton that started before S, and at time S it was close to X. It was in the epsilon k neighborhood of X. So in this way, for every point Sx, I get, I will call it approximating sequence of trajectories from the skeleton. Then I apply measurable selection to this sequence and take it at time t. So this is the definition of psi, and I want to show that psi is the flow we're looking for. So first, why it is measurable. The mapping psi is a composition of two mappings. So the mapping that that computes f at time t, it is continuous in the metric of space X, so it is measurable. Now we consider the mapping that takes Sx omega into the sequence of approximating trajectories. So its measurability follows from the following representation. So we fix, it is enough to fix the index of trajectory, and this event is clearly measurable. Okay, so we get some object that measurably depends on all arguments. And now I want to verify the strong flow property for this object. So first, we observe that if I consider the point Sx that is already on the skeleton, then the approximating sequence, it is a constant starting from some moment. So my measurable selection mapping will give me the limit. And psi stx will be equal to yn of t, where yn is such that yns is equal to x. Okay, and the next case, assume that that Sx is not on the skeleton. Then by k I denote the degree of x, and consider some compact neighborhood of this point, which is the union of intervals. Again, we can apply this property that of dense trajectories that from the past, and get some kind of this construction. So here I have a compact neighborhood, and I choose trajectories that stay on corresponding edges for some amount of time before, so from S minus delta to S plus delta. And as a new neighborhood, I consider this set. Okay, so this set is a it is another neighborhood of point x at time s minus delta, and this is neighborhood at time s. And we observe that all trajectories that passed through K1 at time s minus delta, they coalesced into finite number of points at time s. So these are red points. And x is not a red point. So this leads to the following conclusion. If epsilon k is less than the distance from x to the set A, then trajectories that come close to x at time s, they must start in this time from s minus delta to s. Okay, they cannot start before s minus delta because then at time s minus delta they must go through this new neighborhood, and then they coalesce into red points. This proves that starting moments of approximating this proves that starting moments of approximating trajectories, they converge to s. In particular, this limiting trajectory, it indeed starts at time s from point x. Okay, and the next I want to check that the sequence of approximating trajectories is relatively compact. So the construction is very similar. Again, I consider I consider a neighborhood of a point x, and I can assume that the boundaries of this neighborhood are formed by some trajectories from the flow. Now, if I consider trajectories that were at compact k at time s, then after some time, in my notation, it is s plus delta over 2, I have only finite number of trajectories. So this set is equicontinuous. Also, we know that approximating trajectories for large enough k, they start close to s, and they belong and they start from the set k. So in the neighborhood of x, oscillation of trajectories are at most 2 alpha, and after time delta over 2, oscillation is small by equicontinuity, and because we have only finite number of trajectories. So this proves relative compactness. From this, we have the following, we can prove the strong flow property. So if we consider 3 moments of time r as t, then by construction, if we consider some moment r1 between r and s, then approximating trajectories must coalesce into finite number of points at time r1. And our measurable selection mapping will choose one of them as the value of the flow. So for all points u after r1, the flow will follow some single trajectory from the skeleton. And when I apply the flow to the value on the skeleton, I must the flow just follows these trajectories also by construction. And so we get the strong flow property. Okay, so this is about the theorem. Some remarks. This construction, it is actually can be applied to smooth flows because for flows that have continuous modifications, this measurable selection just gives give a limit of approximating trajectories. And so in some sense, this approach unifies both coalescing case and diffeomorphic case. And the second remark is that in the paper by Evans, Morris, and Sen, some sufficient conditions were obtained for the instantaneous coalescence property. So in this paper, they considered independent Feller processes, independent identically distributed Feller processes, and these are sufficient conditions when the instantaneous coalescence is satisfied. In their case, they have a compact metric space. So with respect to some probability measure, it has the measure of the ball is proportional to the power of radius, and transition probabilities, they have density with respect to mu, which is symmetric and has such estimates. Okay, and also yeah, so under these conditions, they proved that there is an instantaneous coalescence property. So in my next talks, I will give some examples. So this is the work. This is the ongoing work. So we want to construct some flows from coalescing Walsh-Brownian motions, and also to generalize this construction to get strong flows of kernels. In the paper by Lejean and Raymond, it was proved that when we don't have a coalescence property, so when the flow can split particles, then one can obtain the following representation for finite point motions. In terms of flow of kernels KST. So they were able to construct a weak stochastic flow. It seems that the presented construction is general enough to give some hope to get a strong stochastic flows in this case. And I think this is all that I wanted to say today. So thank you for attention.
Thank you. Maybe some questions, comments, please.
Georgi, I have a question. So when you considered some sort of Markov property, you had it for skeleton process. Is
Yes.
it correct?
Yes.
But then you defined your flow for all S and X. And do you still have this strong or just Markov property for extension with the same filtration?
It will hold for the filtration of the flow. So here I will show the choice of epsilon k. In the paper by Lejean Raymond, they choose epsilon k in a special way, so that like for fixed S and X, we have almost sure convergence of Y to the limit.
But you at first select epsilon k and then take?
Yes, so it can be selected such that for each S and X, we have this almost sure convergence.
And this exceptional set is independent of S and X, correct?
No, it depends on S and X, but it is enough for the distribution, to get the correct distribution.
Okay, thank you.
Georgi, I have a related question because considering your construction and not at the first time, I must say, I always try to find the place in this construction where we lose good properties of the noise. It seems that it heavily depends on the this property that every compact turns into the finite set of points for which time, when, maybe it will be interesting to get an examples of other coalescing flows than Aratia flow with a good noise.
Yes.
Maybe even if this coalescence will be artificial, like we add some Poissonian or compound Poissonian process just to check when we have coalescence, something like this one. Okay.
Yes, thank you.
So if there are no other questions, let's thank our speaker and see you next week. By the way, Georgi, maybe you know who will be the speaker.
Sharipov.
Okay, so then bye, up to the next week. Bye.
Thank you. Bye.
Thank you.
Bye-bye.
Thank you. Bye-bye.